Hello everyone, this lecture is about the Georadar or ground penetrating radar. On this picture you see a man walking in the grass carrying something that looks like a mower. But it's not a mower. This is a GPR, ground penetrating radar, in action. So actually this guy is walking around, and by carrying this instrument on the grass, he's measuring properties of the subsurface and trying to reconstruct the structure of the subsurface. So the ground penetrating radar is a non-destructive way to probe subsurface properties. One advantage of this approach is that it usually requires a light equipment, as on the preceding pictures, like a mower. The results are directly obtained, and you see the guy actually has a screen here. Part of the post-processing is included, so he can observe directly the subsurface. Another advantage of the GPR, in contrast to the magnetotellurics MT from the last course, is that the method is based on an active source. So a source is emitted and the parameters of the source is controlled. So here are some examples of application of the Georadar. There are many applications in geosciences, including resources prospection in applied geophysics, or remote site detection in archaeology, analysis of glacier and bedrocks in glaciology, or snow studies. In civil engineering, it can be used to control the quality of concrete, pavement, bridges. And it's not only that, it's actually much more. It's used a lot by militaries. So, for example, to detect mines, bombs, or for probing the subsurface to find secret rooms. And it can also be used for finding people or finding persons using a wall penetrating radar. So it's the same as a ground penetrating radar, but on the wall, so you can see through the walls basically with this approach. So here's the quick historical outlook of the GPR. So the ground penetrating radar was pioneered in Germany by Leimbach and Loewy in the years around 1910. So what they did, they put some antennas around the borehole and they emitted and received electromagnetic waves, and they tried to use this to detect the location of mineral deposits and water reservoirs. So the story started then close to the 1930s, Stern introduced radioglaciology, so basically took the Georadar onto the glaciers, and this led to the development of an entire research field to study the structure of ice. And further back in 1972, the Georadar was taken on lunar orbit using the Apollo lunar sonde experiment. So the Apollo lunar sonde experiment allowed to actually probe the surface or the subsurface of the moon using a radar on orbit. So these are examples of structure of a crater measured with Apollo 17 and some interpretation of radargrams made after this. So again, as all geophysical exploration methods, there is a depth sensitivity which is related to frequencies. So you have the spectrum here of electromagnetic waves, from the gamma rays to the long radio waves and the visible light here. So we are somewhere into this range of values, and the lower frequency waves, so they are within 10 and 500 megahertz, are sensitive to depth, so from the meter scale to the kilometer scale. So as on the Apollo lunar sonder experiment, then they could probe the first kilometer on the moon using these low frequency waves. While on the other hand, high frequency wave in the range of 900 to 1200 megahertz are sensitive to shallow depths, so the centimeter scale, and these can be used, for example, to see through walls using a wall penetrating radar. So for the principle, there is basically a transmitter antenna and a receiver antenna. So the transmitter here, a receiver here. This is air, this is the ground, and you have a structure here with a flat layer. There are contrasting properties between this layer of the ground and the second layer of the ground. So the transmitter emits an EM wave with a given pulsation in the range of 10 to 2000 megahertz, and this will trigger a wave that will reflect inside the ground, and that will be recorded. The signal of this reflection will be recorded by the receiver. So that's for the principle. It's very similar to seismic method. Here is in more detail. You see a complex site here with 3 layers with different properties. Here's a site of deposition of Müll and some Rohre and some fundament. So there are lots of things to see in this ground. Someone is up there, is holding a georadar with an emitter and a receiver and a laptop. And thanks to this variation of properties in the ground, there will be some reflections, and it will be possible to analyze the structure of the subsurface. So let's focus a bit more on the soil physical parameters of interest. So of course, up to now we mostly discussed about the electrical conductivity, sigma in Siemens per meter. And now what also matters is the dielectric permittivity, epsilon, in farad per meter. So in brief, this dielectric permittivity is the ability of a substance to hold an electric charge. Then we have waves, and these waves are traveling through the ground and reflecting on material boundaries. The wave propagation velocity can be defined as such. So V is equal to C divided by square root of epsilon, the permittivity. C is the wave speed in vacuum, which is 3 times 10 to the power 8 meter per second, and epsilon is the dielectric permittivity, basically ranging from 1 for air, 80 for water. And we'll see other values for different types of rocks. So basically the waves, the electromagnetic waves, you should remember they travel in vacuum, so they can travel at the wave at the speed of light, basically, c in vacuum, but when they travel through a medium, they slow down in this medium or in this substance. And the slowdown is shown by this reduction, so the velocity will be c divided by the square root of permittivity. So that's a factor of reduction of wave speed with regard to the wave speed in vacuum. So here's a table showing you some examples of magnitude of these numbers. So you see, as stated before, for the air, the dielectric constant is about 1, and the velocity of the wave, here measured in meter per microsecond, is about 300. In contrast, you can see quartz here has a dielectric constant ranging between 4 and 5, 4.3, and a velocity of about 145 meter per microsecond. Other materials, such as salt water, have a very low velocity, so it's about 30, and high dielectric constant. So it's clear that waves are slow in water. They are medium fast in loose material. So you see, for example, in sand here, we have values of about 100 or 50 here, depending on the content of water. But they're also fast in solid. So if you have a very nice crystalline material, like pure quartz here, it's about 150. Or in sea ice and permafrost, you see values that can reach above 100. So since we have these different materials with different velocities, we will have contrast of impedance between the different materials. So again, that's a picture of the subsurface. You see the boundary between two materials. Above, there's someone going around with a georadar, emitting and receiving waves, and these waves are traveling through these different materials. So now we need to define what is the impedance. So the impedance of the material is the square root of mu, the magnetic permeability, divided by epsilon, the dielectric permittivity. So that's defined per material. That's one value per material. If you have two materials, such as here, there will be a contrast of impedance, and that's what will control the reflection. So you see, R now is the reflection coefficient, and it's equal to Z2 minus Z1. This is the contrast in impedance divided by Z2 plus Z1. It's also obvious to see that if Z1 is equal to Z2, this reflection coefficient vanishes. It goes down to 0. So now what happens? If someone is walking, then the distance x will vary, so the horizontal position will vary, and the waves will keep on being emitted and transmitted. So it will be possible to record the position of the reflector or the time at which the reflector is reached as a function of the distance. So at this position here, the reflection will be reached faster or shallower than at this position in x, where the interface is much deeper. So in practice, what is obtained is what is called a radargram. And it is constructed as a collection of traces. These are the traces, what is recorded during the travel. So we have the horizontal distance, and this is one trace per position in x. These traces are natively in time, so this is double time travel, travel time, but they can be migrated to depths upon some post-processing routines. So that's An example of a nice radargram. So it's an example of a survey made in a folded rock sequence. So you see a nice outcrop here with a folded strata here, which is outcropping, and here's the trajectory of people doing radar measurement. And these are some of the results that can be obtained. These are radar measurement made with a given frequency of the source. So here you see 200 megahertz, and these are obtained results. So you can recover, for example, the shape of the strata. We see the folds, which can be observed in the outcrop. They also, of course, continue below the subsurface. Another example here is a complex stratigraphy. So we have a stratigraphy with different layers and erosion surfaces. So you see alluvial fans in the surface, some river terrace in the bottom of the sequence, and different types of loose sediments that are stacked in between. So next to this outcrop, a section can be taken, and this is again a radargram that can be interpreted, so we can reconstruct the different interface within the subsurface. So the alluvial fans can be traced down, and the river terraces can be traced down at depths. The thickness of the layers can be also reconstructed. Another way of doing georadar can also be an airborne survey. So this is also nicely, it is also quite popular. And yes, no, it's not a rocket. So that's a huge radar tool of the BJR. And this is the helicopter that's going to carry this measurement tool. You see it here. Here's the helicopter of the BJR, and you see here the tool, the recording tool that transmits waves and receives waves above the subsurface. So this is something even more evolved than just carrying a material on the surface of the Earth. One can go with a helicopter and actually do georadar measurement above huge areas. An example here is the study of the ice cap in Greenland. So you see, for example, the map of Greenland is here, and the red box is showing you this map here. A lot of different lines are showing trajectories of helicopter flight path, and these are some results of the measurements. So you see different sections here through the ice. We can recover the internal layering of the ice, and the structure of the base of the ice, so the bedrock top, can be nicely imaged. So you see the variation of depth of the bedrock at different locations, and the internal structure of the ice, which is nicely resolved by the radar. It's also quite a popular method to study the structure or the inner structure of sand dunes. So that's an example in Namibia, in the desert. One can also carry along the ground penetrating radar on the sand dunes and basically image the lamination of the sand beds. One can then reconstruct the entire structure of a sand dune and interpret the kinematics or the evolution of the sand dunes with time. It's also used a lot for tracing or prospecting for mineral resources. So you see different types of examples here, all taken from a single review paper. You see, for example, a georadar measurement across a region which was which contains a kimberlitic dike emplacement. So we have a structure of the rock which can be traced, and inside the region of kimberlite, the traces are erased because the kimberlitic eruption has completely disrupted the internal structure here. So we can trace the position of the kimberlite dike. Here is an example of a bauxite deposit in a sedimentary layer in Australia. So you see a nicely marked horizon in the subsurface, which is the location of a bauxite deposit in the sediments, and other examples of a thin flat coal deposit, which are marked by very strong reflectors and very flat reflectors here in this example. A nice and last example is, for example, the use of georadar in archaeology. So you see an example here of the Roman settlement of the Faleri Novi in Italy. So it's a Roman settlement that dates 241 before Christ. So you see the map here. Roma is here, and Faleri Novi is 50 kilometers north of Rome. If you have a look, that's a satellite or aerial view of the site, you don't see much. So that's basically a field here. And what the authors of this paper have done is a radar survey. And so you see the aerial view on one side and the radar view on the other side. They carried out a high resolution radar survey, and you see a lot of structures in there. And in fact, if we zoom on some parts of this radar image, one can recognize the structure of the different buildings that used to be part of this town of Faleri Novi. So you see the structure of the buildings, their shape, the location of different rooms, and the connection between the different buildings. And this helps to, for example, reconstruct ancient cities, and for example, to figure out where the temples are, the markets were, where the baths were, the theater. So all these structures can be traced thanks to the georadar. So as a summary, the georadar emits electromagnetic waves in the subsurface. The propagation speed depends on the nature of the material. When we have contrasting properties in the subsurface or contrasting impedance, reflection will be triggered. The recording of the traces and the plotting of the traces versus the distance is basically a radiogram, and this radiogram can be interpreted to reconstruct the structure of the subsurface. There are many applications of the georadar in earth and environmental sciences. It's relatively shallow prospection method, so it is really complementary to other geophysical prospection methods we discuss in the lecture. That's it for today.